Welcome back to another Regents Physics Mechanics review. This will be the free response questions from the 2022 June exam. So with this, what I did with these questions is I broke them up into parts. On the exam, they are all like individual questions. In the brackets, they have like a 1 or a 2 next to them. That's just telling you how many points each question would be worth on the Regents exam. So let's get into our first example. All right, so this is example number 1 for this portion of the review. Is example number 17 in your packet. So a 55 kilogram ice skater slides across a level surface, and the force of friction acting on the skates has a magnitude of 11 newtons. Part A, which would be one question on the Regents, it tells me to determine the magnitude of the weight of the ice skater. Part B, calculate the coefficient of kinetic friction between the ice skater and the ice. Show all work, including the equation and substitution with units. In the brackets, this tells me it is 2 points. I'll show you what is 1 point, and I'll show you what is the other point when we do that question. So this is part A. Let's start off with this. Determine the magnitude of the weight of the ice skater. So we have here what is weight. It is not just the mass of the object, it is the mass and the acceleration due to gravity on whatever it is, the person, an object, the block, whatever it's going to be. So for this one, we have here a 55 kilogram ice skater. So we had to use the 55 kilograms and the acceleration due to gravity on Earth because it doesn't say where anywhere else. So how did I determine to use the mass and the acceleration due to gravity? If you look for weight on the reference table, you will find it in the mechanics portion. With that, you will find that weight on the right side, it has a bunch of variables, and it tells you what those variables mean. If you look on the right side, you will find weight at 1 point. You will find that weight is equal to F subscript G. This is really equal to mass times gravity. On the reference table, it is G equals Fg over m. Just move m over and you end up with Fg equals mg. Alright, so now we're going to just plug in what we have here. In the question, it gives me that I have 55 kilograms, so the mass is equal to 55 kg. My acceleration due to gravity g, that is on the front page of the reference table. That is 9.81 meters per second squared. So what I'm going to do now is just plug this in to the equation. So you have Fg equals mg, so 55 kilograms times 9.81 meters per second squared. We're just going to plug this in to the calculator and end up with 55 times 9.81. End up with an answer of 539.55. What you're going to do with this, you can keep it as is or you can round it. Either answer would be acceptable in that situation. What I'm going to do just for easier math later on is just round it off to 540 newtons. If you chose to use 10 meters per second squared, that was also an acceptable answer for this question. You'd end up with 550 newtons. That was an acceptable answer. You do not need to show all this work for this question, but it's just good practice for a question like part B for this example or this prompt. You just need to show here that Fg is equal to 540 newtons. And that was your 1 point, or if you wrote it out as 539.55, that would have also been acceptable. So part B. Part B, we are being asked to calculate the coefficient of kinetic friction between the ice skater and the ice. With the show all work, including the equation, the substitution with the units, and then of course, the answer. So with this, we are just going to look for an equation that involves the coefficient of friction on the reference table. On the reference table, the only equation that involves coefficient of friction, again, if you don't know what coefficient of friction is, look on the right side of the reference table. you look for coefficient of friction is equal to, or the symbol is equal to coefficient of friction. This is going to be the Greek letter mu. The only equation that involves this is the force of friction is equal to mu times the normal force. So what I want to do with this, I have to recognize what the normal force is going to be equal to, and then I will just then plug in to the equation with my units and end up with the answer. So quickly just going over what the normal force is going to be equal to in this situation. It doesn't tell me anything about any angles or anything. So really, when there's no angle, the normal force is going to be equal to the force of gravity. I can show that real quick doing Newton's second law. So if I wrote out a little free body diagram, making a dot here, the force of gravity goes downwards on the person. The normal force then must push up. These are going to be equal to each other. Obviously, there's also a force of friction. Say they go into the right, the force of friction is in the opposite direction of the velocity. So just quickly doing Newton's second law here, F net equals ma. For Regents, the sum of all forces equals ma is just a better way to write it out. We're looking at in the y direction, so subscript y. It doesn't say anything about me moving up or down, so we'll assume that the acceleration is 0. So anything times 0 is 0, so that whole right side of the equation is 0. On the left side of the equation, I have my vectors for the free body diagram. So going upwards, I have the normal force. That is Fn, so that is a positive vector. Going downwards, I have the force of gravity, so that is a negative vector, Fg. That is all going to be equal to 0 on the right side. A little bit of algebra, just add an Fg to the other side. I end up with the normal force is equal to the force of gravity. So that's what I'll be plugging in later when I do the equation for the coefficient of friction. Now I have to show, to solve for the coefficient of friction in part B. So it's being multiplied by the normal force. Do the opposite of that, and I have Fn. Cross that out. I have the force of friction over the normal force, which we just determined is Fg, is equal to mu. All right, my last step here to get my first point is going to be my equation substitution with units here now. So this is all like 1 point based on the rubric of the Regents. Now just plugging in my two things. So I have the force of friction, which is given to me as 11 newtons. So I'll put it next to it. So 11 newtons. So equation. Now this is the FF over Fn equals mu. Now I have the substitution with units. We have 11 newtons over the normal force, which we determined to be the force of gravity. We got that in the first part as 540 newtons, and that is equal to mu. So that part here is all 1 point. Having my equation and then just substitution with units, that's 1 point in the question. My next point is now just being able to put it into the calculator and get the correct answer. So you're going to do 11 divided by 540, and you end up with an answer of 0.02. And there is no unit for the coefficient of friction. You can see that as well. You have newtons over newtons, so those will end up canceling out. Your units cancel. You end up with a unitless quantity for the coefficient of friction. So that's your second point. The 0.02 equals mu. So again, 1 point here is just the writing out the equation, then substitution into the equation, or substituting into the equation, and then again the answer is your second point. So that's part A and part B. That would be two separate, or actually three questions technically on the Regents. So let's move in to our next example. All right, so example number 2 for this set, 18 in your packet. So for these next two examples, what I'm going to end up doing is breaking them up into multiple slides, because I don't want to like squish in all the work on one slide here. They get a little bit longer than some of the others. So this one will be part A, the next slide will be part B, and that will be shown in the chapters of the video. So we'll say like example 18 part A, example 18 part B, and those will be individual chapters, so you can go right to that answer. So what we're working on here is part A. So number 18 is telling us that we have a 100 Newton box is pulled up a 20-meter long incline by a constant force of 80 newtons. The vertical height gained by the box is 10 meters. Part A is asking us to determine the total work done in joules by the 80 Newton force in pulling the box to the top of the incline. All right, so work done. With this, work has multiple equations on the reference table. You either have force times distance or the change in energy total. For this example, we are being asked to do only the 80 Newton force pulling the box to the top of the incline. So if you look at the diagram here, we have this 80 Newton force that is pulling this 100 Newton box to the top of the incline, and it is pulling it a distance of 20 meters up the incline. So what we're worried about is these two values, both the 80 newtons and the 20 meters. You're not worried about that it's going up 10 meters, you're just worried about the incline here. The other thing with this is that the incline is at some angle. We're not given that angle, but it does not matter because the 80 newtons on the incline is parallel to the incline, so it's just FD. You don't have to worry about any angle in there that will change the force that I'm actually pulling the box with. So with this, again, we are trying to find the total work done. It tells us the unit for work, so you don't have to worry about remembering what the unit is. If you don't know the abbreviation for joules, you would just write the full word out. If you know your abbreviation is just J. So what am I given here in order to find that total work? The first thing I see here is I have the 80 Newton force. That is going to be my force. So that is F and 80 newtons. With this question, you also see at the end you have 1 in the brackets. That just tells you this is a 1-point question. It doesn't say anything about showing all work and substitution with units, so you don't actually have to, but it's good practice again to do all of this for the questions that do require it. So you have here is being pulled up the incline, and that is a 20-meter distance. So D is equal to 20 meters, and it's asking me to find the total work done. So W is a question mark. All right, so with this equation on the reference table, work equals force times distance. All I do now is just plug in my force times distance, and I will get the work done and bring it up the incline. So we have here 80 newtons times the distance, which is 20 meters. And now you're just going to plug this into your calculator, and you end up with 80 times 20, and that is going to be 1,600 joules. All right, so let's move on to part B on the next slide. So working on part B here, we have determined the total amount of gravitational potential energy in joules. So again, it gives you the unit for gravitational potential energy gained by the box as it is pulled to the top of the incline. So again, part B. This is again a 1-point question, so you don't need to show the equation. I'll just go through that so it's clearer and you see all the work that goes into it, but you don't need to show all of that work to get full credit on this question. You just need to show the correct answer. So gravitational potential energy was that on my reference table, it gives it to me as change in gravitational potential energy, but you don't need to write it out as that. You just have here that PE equals mgh, or for my AP students, U subscript G equals mgh would also be an acceptable version of the equation. So with this, I said need to determine what I have here in the question and plug it into my equation. So my first thing here is telling me I'm pulling up to the top of the incline. So gravitational potential energy includes height. It tells me that the vertical height gained by the box is 10 meters in the question. It also says that in the diagram as well, it shows it to me as a 10-meter height. So I can put here that H is equal to 10 meters. And then you have a box there that is 100 newtons going up the incline or going up that height. So with the 100 newtons here, what is that going to be exactly? That is a force. We know that newtons is the unit for force. And with that, that is actually going to be the weight of my object. So that is going to be the force due to gravity is 100 newtons. All right, so we don't have in the equation Fg, or like just it's not there as F subscript G. It might be there in another way. So in the equation we have mgh. H is my 10 meters. That's pretty self-explanatory. But we have there mass times gravity. We kind of just did that in the first example with having to find the weight of the ice skater. And we figured out that Fg equals mg. This is on the reference table as well as just g equals Fg over m. So what you have to do here is figure out that my 100 newtons, this Fg, is the same thing as mass times gravity. So I'm just going to plug in to the equation my Fg times my height. So with the Pe equals mgh, the mass times gravity is that 100 newtons. Times the height, which is 10 meters. So just plug this into your calculator and you end up with the potential energy here gained, or the gravitational potential energy. So just do 100 times 10 and you're going to end up with 1,000. And again, the unit for this one is going to be joules. So 1,000 J is going to be my answer. So let's move in to our final portion of this question. So part C, we have explained why there's a difference between the total work done by the 80 Newton force in pulling the box to the top of the incline and the amount of gravitational potential energy gained by the box as it was pulled to the top of the incline. Alright, so with this, it's basically saying that my total energy put into the system in some capacity is not the same as my gravitational potential energy gained. So an equation that I can think of with this that can help me basically explain this is going to be the ET, the E total equation. So ET is equal to KE plus PE plus Q, which is heat energy in this situation. So it's essentially saying that this ET, this total work, is not equal to my gravitational potential energy gained. So there has to be some other type of energy in order to balance this out because energy has to be conserved. So my 1600 joules put in for total work is not equal to 1000 joules gained by potential energy due to gravity. So all I have to do with these is then figure out what type of energy, or explain that there is some other type of energy present in the system due to either kinetic energy, which would be if there's some kind of speed here. It says we have a constant force, so we have some speed going up the incline and we're not accounting for that with the potential energy. Or since it doesn't say this is a frictionless surface, we can say that there is friction on the incline as well. And that was actually one of the answers for it. You can literally just put down friction and that would be enough actually. You don't have to even explain it. You just need to write down friction. That was enough for 1 point on the Regents for this last year. What I'm going to do with this is explain it. I'm going to type it out on the next slide. So I'll show this as it will be one part on the chapters, just so it's a little bit clearer and my handwriting doesn't get in the way of writing it out. But basically, you don't really have to even explain it. You can just say that we didn't account for kinetic energy and just leave it at that. You can say that there was friction on the incline and just leave it at that. I'll explain it a little bit more to say that there might have been friction on the incline, and due to this, we had heat energy. So that is the missing piece between like the 1600 joules of the total work done and the 1,000 joules of the potential energy due to gravity that we gained going up the incline. So again, next slide, I'll have this all typed out. Essentially, just writing this out here, for part C, there could have been friction in the incline, so some of the total work on the system might have been to overcome friction, heat energy. So that's why you didn't have the total gravitational potential energy wasn't equal to the total work. This is really all you needed. Again, one of the answers for the answer could have just been you could have literally just wrote down friction, and that was worth 1 point on the Regents. You need to even explain it at all. There didn't need to be an explanation, even though it says explain. The answer could have been friction, and you would have got full credit for this. So let's move in to our next example. All right, so example number 19. This is the last example in the physical version of the packet. In the digital version on Google Classroom, I have added in one more example that might be helpful that also has to deal with projectile motion. It is not similar to the one in the multiple choice. When I first looked over it, I didn't look at it closely enough. I was just glancing and saw it was projectile motion, so I kept it out of the packet originally. It's in there now, and it'll be in this video. For this question though, same idea. We're going to break this up into multiple slides here. We have part A, part B, and part C. So this one we're going to work on part A, and I will show that again in the chapters of the video in the progress bar. So we have here a spring with a spring constant of 2600 newtons per meter. It's compressed 0.1 meter from its unstretched position. The spring is then released, propelling a 3 kilogram block along a horizontal, frictionless surface. This block then collides with a stationary 1 kilogram block. The blocks remain joined and move together as shown in the diagram below. The one in the packet, it's the diagram straight from the exam, so it's like stacked on top of each other, just so it can fit better in the slide here. They are all next to each other, but it shows the three portions of the system here. So I know this kind of seems like a lot at first, but really with each part of this question or each like question from this question, it really tells you exactly what to do and what's happening at each part of the system. So you don't have to kind of like do it all at once. For my AP students, you've seen this type of question before where you have to pretty much do it all at once. It's not broken up like this. So this might seem a lot easier for you. For the Regents students, again, it pretty much breaks this up into each part and tells you exactly what to do at each part when the spring is compressed, when the spring is when the system is before the collision, and then when the blocks collide together. So what I have here first is determine the total amount of elastic potential energy stored in the spring when the spring is compressed 0.1 meter. All right, so elastic potential energy. What is that going to be? So let's look at the reference table again. It's asking us to determine the total amount of elastic potential energy stored in the spring. This is also known as spring potential energy or potential energy of the spring. Look on the reference table, look on the right side, and look for an equation that involves elastic potential energy. You are going to see here that we have PES is equal to 1/2 kx squared. So now you just want to see what you have in the equation and then figure out what you're given in the question then to determine your answer. So the first thing here, what do we have in the first part of the question? It tells us that we have a spring constant of 2600 newtons per meter. That is the K in the equation. It tells us this in the reference table as well, that K is my spring constant. So I have here that K is equal to 2600 newtons per meter. The other thing I have here is x. That is going to be my displacement of the spin. It tells me this in the question in both part A and in the prompt that we have 0.1 meter. The same exact thing in part A. It tells us that we are compressing the spin 0.1 meter from its equilibrium position, or its unstretched position. That is going to be my displacement. So x is 0.1 meters. All right, so now all I have to do is plug it into the equation and get my potential energy due to the spin, or potential energy of a spin. This is then equal to, so PES is equal to 1/2 K, which is 2600 newtons per meter. I have there 0.1 meter raised to the second power. I'm going to do that one. So I'm going to do two steps here. First, I'm going to have here 2600 divided by 2 is going to be 1300, and do the 0.1 raised to the second power. So going with this again, moving it up here, I have PES is equal to 2600 times 1/2 is 1300 newtons per meter. Then 0.1 squared is 0.01 meters squared. So I'm going to end up here with 1300 times 0.01. So multiply those two together. I'm going to end up with the potential energy of the spring, or the elastic potential energy, as just 13 joules. So that is my answer. Again, I didn't need to show all of that work because it was only a 1-point question. It didn't tell me to show all work, including the equation and substitution with units, but it's good practice and it's good to show you where I'm going with this question. So the answer here is just 13 joules. So let's move into part B. All right, so part B says that assuming all the spring's energy is transferred to the 3 kilogram block, calculate the speed V1 of the 3 kilogram block immediately after it's repelled by the spring. This one says show all work, including the equation and the substitution with units. So part B. All right, so all this is saying, this is a conservation of energy situation. It's telling us that the spin's energy will turn into the kinetic energy. Just based on conservation of energy, real quick, the ME initial is going to equal the ME final. So initially, I have my potential energy, initial plus KE initial equals PEF plus KEF. So a better understanding of where this comes from. They tell you exactly where it is, but let me show you where they're coming from with this. So initially, I'm at rest when the spin is compressed. There's no velocity. It even shows us in the diagram. When the block is moving, it gives you a velocity vector over it. So initially then, I have no kinetic energy, so that's why I have that as 0. I have the potential energy of the spring, so that's my initial potential energy. Afterwards, my spring is then fully stretched out to 0.1 meters. That's the before collision part of the diagram, and my block is moving with some velocity v1. So at that point, I have no more potential energy because I'm not gaining any height. My spring is back to its unstretched position. So this is 0, and I have a velocity, so I have kinetic energy. So that's where it actually comes from for my potential energy is then equal to my kinetic energy. So PES is equal to KE. So now I can actually show this. So my potential energy of the spin is going to be equal to my kinetic energy. So I'm really just now solving for this. So when I go into the equation, KE, what is KE? So PES is equal to what KE is, and that is 1/2 mv squared. So now I have to do, because I already have the value for PES, so I need to write out the equation again. So all I need to do now is solve for V, and then plug in my numbers that I have, and I will then get the answer for V. So solve for this algebraically at first. What I have attached to V squared is 1/2 m, so we're going to divide that out from both sides of the equation. So PES over the mass, divide anything by 1 over something, usually multiplying it. So I have 2 times the potential energy of the spring over the mass of the object is equal to V squared. Last part here, I have the velocity is a squared factor, so do the opposite of that and take the square root of it on both sides of the equation. So I end up with the square root of 2 times my original potential energy in the spring. Let me make that a little bit bigger so it encompasses everything. 2 times the potential energy of the spring over the mass of the block is equal to the velocity. So now let's just plug everything in. So we have here the square root of 2 times what do I have in my potential energy from part A. If you want to go back to that part of the video or you wrote it down, that is going to be 13 joules. Over the mass of the block, which is 3 kilograms, that is equal to my velocity. So on top we have 2 times 13, that is over 3 kilograms. So just plug this into your calculator all at once, or you don't do it all at once, you can do it in multiple steps. I don't have enough room to show all the work here, but 2 times 13 is 26. Divide that by 3. So you should get here that the square root of 8.67 or 8.66 repeating is equal to V. If you plug that into your calculator, that is going to give you that we have a velocity of 2.94 meters per second equals my velocity V1. So that's all the work you'll have to show for that. Showing the equation, substituting in with the units, and then getting your answer here as 2.94 meters per second. That is going to be V1 here. So now we're going to move into part C. All right, so moving into part C of this question, we have here calculate the speed V2 of the 2 blocks after the collision. Show all work, including the equation and substitution with units. So that just means, again, I have to show everything in this question to get full credit. I'll talk about what one point is and what the second point is. So again, here, starting off with part C, you want to find the speed of a system after a collision, or speed of something in the system after a collision. So again, thinking about this in mechanics, you have a collision. So what is the best way to find speed when you have a collision? That is going to be the conservation of momentum. Whenever I have something that is colliding, think about conservation of momentum. You're not going to really have conservation of energy for that, even though the total energy of the system is conserved. Some can be turned into heat when you have that. So kinetic energy is not always conserved, so don't worry about that. Worry about conservation of momentum when you have a collision. So what is conservation of momentum on the reference table? It is going to be that P before equals P after. What is P again? P is momentum, and that is mass times velocity on the reference table. Alright, so let's look for some masses and some velocities. So the first thing we have here, we have my 3 kilogram block. That is going to be mass M1 in this situation. That is 3 kilograms. Mass M2 is going to be the other block, the 1 kilogram block. So M2 is 1 kg. So what else do I have here? I just found a velocity in part B of the question, and that was a velocity for the 3 kilogram block. So that is V1, that's the velocity that goes with my first mass, and that is going to be 2.94 meters per second. I then also have a velocity that goes with my second mass. It tells me that originally my block is going to be stationary. Yes, we have in the begin, this block then collides with a stationary 1.0 kilogram block. So that is going to be V2. And since it is stationary, that means it is at rest. At rest is 0 meters per second. I know that says in part C we'll solve in for V2. I'm going to show you what my version of that variable is going to be in a second. So we have here, that's everything before. Now after the collision. None of my masses are changing, so we're not going to worry about those. It is really just the velocity that is going to change. So it determines whether we're looking whereas you're looking for one velocity, we shouldn't be looking for two. But do we have two velocities after the collision or two momentums, or do we have one? So it talks about in the beginning that the blocks remained joined and moved together as shown in the diagram below. That means that they collide and they stick together. So we don't have a bounce apart question, we have a stick together question, which means we only have one velocity afterwards. What I'm going to call that is V prime, and that is a question mark. So when it talks about V2 in the question there, we're just going to make that V prime for our purposes. So P before equals P after. Now writing out my equation here is going to be M1 V1, because again, momentum is mass times velocity. I have two separate blocks beforehand, so I have two separate momentums, even if one of the momentums will be 0. So M1 V1 plus M2 V2 is then equal to, after the collision, the two blocks will end up sticking together. So essentially I have one momentum after the collision. So I just have M1 plus M2. That's going to be my one mass times my new velocity V prime. So in the before, for M2, we know that that velocity that goes with it is the 0 meters per second. So this is going to be 0 because V2 is 0. So really I'm just left with M1 V1 is equal to M1 plus M2 times V prime, which is the V2 that we are solving for within the question. All right, so looking at this, I want to get that V prime by itself on the right side of the equation. So what I'm going to do with that is being multiplied to M1 plus M2. So let's divide this out from both sides of the equation. So I should be left with M1 V1 all over M1 plus M2 equals V prime, which is the V2 in this situation, what I'm solving for in part C. So M1 V1, now let's plug everything in. My mass is going to be 3 kilograms, that is M1, times my velocity, which is going to be 2.94 meters per second, all over M1 plus M2. It's really 3 plus 1, so I'm going to write it out as 4 kilograms. So that's what I'm going to have here first. That is equal to my velocity when the objects move together. So moving this up here, I'm going to have 3 times 2.94. If I plug this in to my calculator, I'm going to end up with 8.82 kilograms times meters per second, all over 4 kg. That is going to be then equal to, make this line a little bit smaller. that is equal to v prime, or my velocity after the collision. So now just divide these two numbers, 8.82 over 4 kilograms is going to be 2.21 meters per second. Or really, for this situation, since they're asking for V2, I'll just put it as 2.21 meters per second equals V2, just because that's what they're asking for in the prompt. So 2.21 meters per second is going to be my answer there. That is the velocity for the blocks after the collision. So again, the 1 point there is showing the equation substituting in, and the other point is having the 2.21 meters per second equals v prime, or v2, because that's what they asked for. That's the subscript that they decided to use for my velocity. So that is my answer. So let's move in to our final example. Right, so this example was not in the packet, but after looking back through the test, I felt like it was important to go over. So with this one, this is going to be a projectile motion question. It gives you the diagram here. Again, I'm going to break this up into multiple slides and go over it as each part in the chapters. So part A, part B, and part C. So part C actually could probably be done with part B, because it's not that much of a not much to do with that. What we have here is a group of students constructs a catapult that launches a ball at a target placed on a lab bench. The students measure 0.8 seconds from the time the ball is released until it strikes the target, located a horizontal distance of 2 meters from the release point. The ball reaches a maximum height at point P, which is 0.78 meter above the ball's release point. The target is the same height as the release point. Neglect friction. Part A. Calculate the horizontal component of the ball's initial velocity. Show all work, including the equation and substitution with units. Again, so you have to show all your work with this one. But with this diagram here, it doesn't tell me at all what my angle is. So I can't just do the easy way and just plug into just cosine and figure out what the initial horizontal velocity is that way. I have to use what I'm given in the question in the horizontal direction to figure out what that initial velocity is going to be. So the first thing that's going to jump out to me here is that the ball is going to go 2 meters in the horizontal direction. So that's going to be my displacement. So that's going to be d, is equal to 2 meters. What I'm also given here in the horizontal direction, that's for both the horizontal and the vertical, I have a total time of 0.8 seconds. So time is equal to 0.8 seconds. One other thing that I know in the horizontal is that my acceleration is going to be 0 meters per second squared. So I have acceleration is 0 meters per second squared, and I'm trying to find VI, initial velocity. So let's look for an equation that involves all of these in the reference table, and then you're going to find your initial velocity from that. So I have displacement, I have time, I have acceleration, that's just a known quantity, and I have, or I'm looking for, my initial velocity. So look at the reference table. This will line up with my displacement equation. So d equals VIT plus 1/2 AT squared. And if I'm looking at this equation, I can look at the right portion of it where it's 1/2 AT squared. My acceleration is 0. Everything after the addition sign is being multiplied by that acceleration. So that whole part can be taken out, because anything multiplied by 0 is 0. So all I'm really left with is d equals VIT. So now I just want to solve for VI. So VI is being multiplied to time. So let's do the opposite of that. So the opposite of that is dividing it out. So divide out the time from both sides of the equation. So d over t is going to equal my initial velocity here because I have no acceleration. Let's just plug in to the equation now. My displacement is 2 meters in the horizontal direction. My time here is 0.8 seconds. And my initial velocity is VI. That's what I'm looking for. 2 over 0.8. And you should end up with your initial velocity. So 2 over 0.8 is going to give me 2.5. And my units are meters per second. So my initial velocity in the x direction is 2.5 meters per second. 1 point here is for showing the equation and then substituting in the 2 meters and the 0.8 seconds. And then my last part of the answer here is the 2.5 meters per second. That is my initial velocity VI. So let's move on to part B of the question. All right, so working on part B and part C as well, because there's not a lot to do with part C. So part B, we're going to calculate the vertical component of the ball's initial velocity. So same idea, we're going to show our work, include the equation and substitution rate units. And the same idea with this question, this part of the question, we are not given an angle. So we have to use what we're given in the y direction or the vertical direction in order to figure out what my answer is going to be here. So what I have here, I'm given that I have a displacement to my highest point of 0.78 meters. So that's my max height. So I can put displacement is 0.78 meters. I also know in this direction that my acceleration is going to be negative 9.81 meters per second squared. What else do I have here? I don't have really anything else for the most part besides that I have a total time of 0.8 seconds. I actually do have one other thing that goes along with this. I have 0.8 seconds. I know to get to my highest point, just like in a thrown up free fall problem, I throw up something, my total time is 0.8 seconds. To get to the highest point is going to be 0.4 seconds, so t over 2. A total time over 2 is going to be 0.4 seconds. Then I know at the highest point that my velocity is going to be 0 meters per second. So VF is equal to 0 meters per second, and that is going to be at the highest point. So really I could put time actually, even though it's t over 2, which is going to be time in this situation. So I'll put next to it t. That time, which is t over 2, is going to be 0.4 seconds. That's what we're going to end up using in this question. Because I have acceleration, I have the time to get to the highest point, I know the velocity at the highest point, I can find the initial velocity based on that, because that equation is going to end up being my final velocity equation. So I want to have acceleration, I have time to get to that highest point, I have the velocity at that highest point. I can then find the initial velocity based on that. So my displacement, not needed. I can use a different equation to use the displacement. But for this one, I'm going to use the 0.4 seconds to get to the highest point. So again, that equation is VF equals VI plus AT. So I want to solve for my initial velocity. It's being attached right now to an addition sign with acceleration times time. Just do the opposite of that, subtract it from both sides of the equation. So I should end up with my final velocity minus acceleration times time equals my initial velocity. So now let's just plug everything in. My final velocity is 0 meters per second. Subtracted my acceleration, which is negative 9.81 meters per second squared, times my time, which is 0.4 seconds to get up to my highest point, and that is equal to VI. So now just plugging this into my calculator here. really with this is keep, change, change. So it's just 9.81 times 0.4 plus 0. So that's going to remain what it is. So 9.81 times 0.4 should give me my answer here of 3.92 meters per second equals my initial velocity in the y direction. So this is for part B. Now working on part C. This is just in the diagram here. So looking at the diagram, draw an arrow originating at point P that represents the direction of the ball's acceleration. All right, so we've done a little bit of acceleration in parts A and B. So now we're just drawing the arrow that represents this at point P in the diagram. In this part, we have here that my acceleration is negative 9.81 meters per second squared. In part A, I have my acceleration, the horizontal component is 0 meters per second squared. So there's no acceleration in the horizontal, so there's no vector for that. There's only going to be a vector for, or an arrow for my acceleration in the y direction. That is a negative acceleration, so it's going to be straight down. Again, that's the direction of the force. The force of gravity will also be straight down. So we have here at point P, just going straight down. That's it. It doesn't say to label it in any way, so just draw the arrow. It's going to be straight downwards. In the answer booklet, you would have like a dot to draw it on. So in this situation, it's just going straight downwards. That's my acceleration due to gravity. That's the only acceleration that is present on the ball, because the only force that is present on the ball is the force due to gravity. All right, so this is the last part of the mechanics review. I hope this was helpful. I'll add this in to the digital version. So if you want to try this question for yourself, you just want to print out that page. It should be its own page. So you just want to print out that page and try this question for yourself. You can do that, and I'll make a announcement for that in the Google Classroom as well. So I hope this was helpful for you guys, and see you guys in class.